Hello, everyone. Thanks so much for joining our talk today. So the topic we want to share today is Trustless Attestation service where zero-knowledge proof. So this idea is actually still in an early stage, and we want to explore it further. So if you are interested in it, if you have some suggestions or want to discuss about it, feel free to reach out to us after the talk. And my name is Donghang. I'm a research scientist in Privacy Innovation Lab of TikTok. This is the agenda today. First, I will give a brief introduction about what is the attestation service. Then I will talk about what is the trust problem of the current structure. Then I will give a brief introduction about what is zero-knowledge proof and how it can help solve the trust problem that we will mention very soon. So let's begin with our system model. So here we are assuming a scenario where we have a client. So we call this client the relying party. The client may want to run some computations on T, and T might be hosted by some cloud provider. So in this sense, we will have these several entities. The first one is the relying party, which is our client, and the second one is the T. Of course, we also have a hardware manufacturer who produces this T. And meanwhile, we will also have a cloud service provider who hosts this T. So that's our general, that's a general scenario that we are interested in. So here, one of the thing is that before the relying party actually sends the private input to the T to do the computation, the relying party actually wants to check whether this T meets the security guarantee first, if this T is trustworthy. So usually what's happening is we have this attestation service. So the first step, the relying party will send the request to the T to say, hey, I want to run some code here. So please prove to me that you are trustworthy. Then the next thing is the T may provide some evidence. And here we have this party called attestation service. So this service is usually hosted by the cloud service provider as well. So T will send some evidence to the attestation service, and this evidence can contain a lot of things. For example, it can contain the hash of the code to make sure the code is actually what the client wants to run. Also, it can contain things like firmware version to check if the firmware version is latest enough. Of course, it contains the signatures of the whole evidence to make sure this evidence is really sent by this T. So this is the evidence, and also attestation service can also get input from manufacturer about the policy. For example, policy can figure out what is the least version of the firmware. So the attestation service will have these two inputs and do the attestation. And next one is the attestation service will simply return this attestation result to the relying party in the form of a attestation report. So one thing we want to mention here is that you see this evidence actually, it contains nothing private. So theoretically, T can also send all this evidence directly to the relying party, and relying party can do all the verification. However, in many scenarios, the user of the T may not have sufficient knowledge about the T or even about the computer. So if we just send this hash from a version, a lot of things to the relying party, it might be challenging for the relying party to do the verification by himself. So that's why the cloud service provider also provides the attestation service for them. Then it's very convenient for the relying party. Relying party will only get this kind of binary result saying whether T is good or not. So very convenient for the user, but it also introduced some problem. Now the problem is now we have a larger trust boundary. In the ideal world of T, we only want to trust the T manufacturer, but here the reality is that you also need to trust the attestation service. Since what if the attestation service returns you a positive result even when the T is bad? So now we have a larger trust boundary, and this, of course, means larger risks and larger attack surface. So I think actually in most cases, maybe cloud service providers are actually good. We don't need to think about them as malicious. But what if just after some software version update, their attestation procedure becomes buggy. So this is kind of, we are putting some unstable thing in the trust boundary, which might cause some problem. So our goal is we just want to exclude the attestation service from the trust boundary. So the trust assumption is still we only want to trust the hardware manufacturer. And the way to do it is we want to apply some cryptographic proof with the attestation service. So the general idea is attestation service also need to generate some cryptographic proofs to guarantee that the attestation procedure is done correctly. And also on the relying party side, it simply verify the proof to see whether this attestation service can be trusted or not. So I will very quickly give an introduction about what is zero-knowledge proof. So it is actually a cryptographic scheme to allow a prover to prove some argument to the verifier. So in this protocol, we actually have two entities, one prover and one verifier. Prover in the T scenario will be our attestation service, and the verifier will be the relying party. So there are a lot of arguments that the ZKP can prove. For example, the argument could be as simple as the prover knows some value. Or in some other scenarios, this argument could be that the prover computes some circuit or a function correctly. So zero-knowledge proof actually is getting more and more efficient. On the right-hand side, you see the timeline here. So the idea actually came out very early, but at the very beginning, it is not efficient at all. So even one single operation, it takes a lot of cost to just generate the proof. But especially thanks to the development of the blockchain, right now zero-knowledge proof is getting more and more efficient, especially within these several years. A lot of very efficient protocols coming out. And in blockchain, one of the main applications is actually to prove the correctness of the computation. So it's actually the same as what we want to achieve here. So for example, Ethereum just used zero-knowledge proof to verify the correctness of the computations, which happens off-chain. So there's one series of zero-knowledge protocol called ZK-SNARK. Its advantage is that it's very efficient, and it is non-interactive. So the prover cost could be linear with the circuit size. So for the circuit conception is like in ZKP, you need to represent the computation you want to prove as a circuit. So that's why the circuit is here. And the verifier cost could be constant, which means no matter how expensive your whole computation is, for the verifier, the computation could be very fast. The verification time could be very fast. And this is actually very good for our scenario, since in our scenario, the verifier will be, relying party will be the client who may not have a good hardware resources. So this is cost-friendly, especially to the verifier. And the next idea is kind of straightforward. For the very naive version, we just apply the zero-knowledge proof in attestation. So this attestation service will do the verification and meanwhile generate a zero-knowledge proof to guarantee that, to prove to others that this attestation procedure is computed correctly. So the thing we want to prove is this attestation circuit, or we want to transfer this attestation process as in the form of the circuit so that zero-knowledge proof can take it as the input. So what does attestation function include? So it varies for various service providers, and it's different for different hardware manufacturer. But in general, it includes the following. So it may include some signature verification to make sure this evidence is really sent by that T, and also some firmware check, also a lot of optional policy checks. So in the most simplified version, we envision the whole circuit as the one on the right-hand side here. So you see there's kind of just a lot of if-else check. If any check fails, it simply will return false, which means this T does not meet the security requirement. And if every check's passed, it simply returns true. So again, this is a very simplified version. What's happening in reality could be more complicated. So now with the zero knowledge proof, the workflow it has a little bit changed. You see, for some zero knowledge proof protocols, we actually require a trusted setup phase, which need to be run by a trusted party or through a secure multi-party computation, which might not be too efficient in this case. So, but fortunately, in our setting, we have a trusted party, which is the manufacturer. So the manufacturer will do this setup phase and generate the corresponding proving key and verification key, then send the proving key to the attestation service, also send the verification key to the relying party using authenticated channel or whatever, as long as it is a secure channel, it's good. So with this, the whole attestation process, actually the process is the same as before. He just sent the evidence to the attestation service. Also, the manufacturer policy will be taken as the input. And on the attestation service side, now it does two things. The first one is the normal attestation. And the second thing is it also needs to generate this zero knowledge proof to show to others that I'm doing this attestation correctly. Then after that, the attestation service will send two reports back to the relying party. One is the attestation report. The other one is the zero knowledge proof. And on the relying party side, they simply check if the zero knowledge proof is wrong, then that basically means there's something wrong on the attestation service side. So either there's a bug or it cannot be trusted. So it's on the cloud, the trust problem is on the cloud service provider side. And what if the attestation report shows something wrong, but the proof is right, then that means this T may have some security issue. So we just want to share with you this idea. We want to put this model very general so that different attestation service or different hardware can fit in this framework. And obviously, there are a lot of space for optimization here. For example, for this zero knowledge proof generation, obviously, you can do parallelization. You can do batch verification. There are a lot of possibilities to make this whole procedure more reasonable and more efficient. So due to the time limit, we will not cover them in today's talk, but feel free to reach out to us to have more discussion here. And this is the takeaway we want to share with you. First one is the zero knowledge proof can be used to eliminate the trust assumption on the attestation service, which we find could be meaningful. And also, we show that most current attestation process are compatible with the zero knowledge proof, so it's feasible. And the third thing is actually zero knowledge proof here actually introduces a new source of trust. So here, instead of trusting the attestation service, you may want to trust the cryptography or math. So in this way, we actually introduce a new source of trust. So we think in T there might be other scenarios where the trust problem may exist, and we may be able to use the zero knowledge proof or use people's belief about math to solve some trust problem. So this might be able to extend it to other scenarios in T as well. So yeah, I think that's everything I want to share today. Thanks for listening.
Ming-Shen, very interesting, thank you. I have one question, well, two questions, I guess. So the first is, how much easier is it for a receiver of these proofs to understand the proof than it is to do the attestation themselves? I think that's one question, because you're transferring the type of trust and knowledge across. So that's the first question. And the second question is, have you done any research or thought about questions like replay attacks and man-in-the-middle attacks?
So for the first question, I think you are wondering what is the verification cost for the relying party to do this verification, right? Yes, yes. So in general, it can be very fast, I'll say. Like we did some initial benchmark.
It's not so much the cost in terms of performance as in terms of knowledge and trust, but understanding the whole.
Oh, right. So in the most simplified case, you can think of this as computing some polynomials and see if some values are equal. So that's the simplified version of the most simplified version of the verification. So I think that's the bar of understanding this verification is kind of not high. So could be friendly to the relying party. And sorry, what's the second question again?
Man-in-the-middle attacks, replay attacks versus.
Man-in-the-middle attack.
I'll touch your file.
Yeah, sure. Thank you.
Yeah, so I have a question actually about the prover cost. So I worked on Snark a while ago, and I remember that with Pinocchio scheme, it takes about 5 seconds to prove just certificate chain with RSA signature. That's what it took more or less back then. So have you done some estimate of how much prover time do you need to actually verify full attestation report?
Yeah, that's a very good question. So I think the question is about the prover cost, right? So honestly, we haven't done this end-to-end test for the real-world attestation service. And for signature verification, actually, it takes like probably the magnitude is like around below 100 seconds. And that could be, in the simplified case, that could be the bottleneck of the kind of the proving phase, since the signature verification is almost the most expensive part for the whole attestation.
And you have more than one, so you need to check a certificate chain.
Oh, right.
Manufacturer,
That's true.
and
True.
you may have additional signed evidence like
Yes.
revocation.
Yes, so for a prover, I think the cost is, we will not say it's to be efficient, it's reasonable. And also, I think there are a lot of ways to optimize it, since in the whole attestation service, actually, there are some kind of verification that you only need to run once. But for some other test, maybe for each code execution, you need to run them. So you can separate them. For the one-time verification, you can do it once, and for all these other verification, you may need to do them each time you do a code execution. So there are definitely space for optimization here. Yeah, that's a good question. Thank you.